Yeah, I can hear you. Thank
Yeah,
you so much.
very much. So you can take the I can hand over to you now from here. Thank you.
Okay. Okay, let me share my screen. Hopefully you can hear me. Uh,
Yes, we can hear you on your screen as well. It's just a bit of but yes, we're good. Yes.
can you see my screen?
Yes, your screen is up for choice now.
Okay. Okay, thank you so much. So, good morning, everyone. So, I'm very happy to be with you. And I remember few years back, I was at DSN in 2018 in Lagos. It was a very good experience. And hopefully you are enjoying so far the boot camp. So today, as mentioned, I'm going to do an introduction to computer vision. So we are going to do that through our small agenda. So first, we are going to take a step back and ask a question, what is computer vision exactly? And then we are going to look at a little bit at the history of computer vision, because it's very important to understand the different steps we have been going through until what we have today in order to have a better perspective of the field. Then I will focus on an operation on images that is called convolution, which is very important in the case of image processing and computer vision. And finally, I'm going to go through an example, a problem we are going to solve together end to end, so that we can have a better idea about how we work on a computer vision problem nowadays. Okay, so after saying that, we are going, sorry, we are going to ask the question, as I mentioned, what is computer vision? So I took this computer vision from Gradsky, who is the person who invented OpenCV, which is a well-known library for doing image processing and computer vision. It has invented it before this AI revolution we are seeing now. So he invented this library since 2000. And he mentioned in his book at that time, he's mentioned that computer vision is the transformation of data from a still or video camera into either a decision or a new representation. So a still, that means so an image that is not moving, or a camera, as we know, the camera is a moving image. So we have many images that are moving in a camera. So I show here an example on the left where you can see a tree, for example, and the decision can be what is inside this image. And the answer for a computer vision perspective in kind of decision can be, this is a tree. And on the right, we have an image on a road where we have some car that are parked on the side. So here we can transform this image in a new representation. And this representation that you see below is what we call a semantic segmentation. So we transform the initial image in another image where we are able to identify with a same color an object or a set of objects that have the same type. Like here you can see on the right, all blue region are in fact cars. You can see, and the road, you can see the main road in different colors, and even the trees. So this is called semantic segmentation, to identify an object or a set of objects in an image. Because as human, when we look at the world, we automatically do this in our brain. So our brain is so powerful, it do it automatically. But from a computer vision perspective, is a more difficult task, in fact. So, and computer vision is, in fact, a very challenging task. But fortunately, we have some very great advances these days. Okay, so after giving this definition of computer vision, so let's look at the history. So computer vision, in fact, is a field that has around 70 years now. So people have been started working on computer vision since the 60s. And at that time, so the main process that have been that has been developed by David Ma. So he developed a framework where he mentioned that in order to solve a problem, a computer vision, because we have an image or a camera, and we want to get some other information, some insight from these images. So he developed a framework where we have to start by what he calls low-level features or low-level elements of the image. So these are mainly detecting what we call edge or line or contour. And then based on that low-level features, we come up with some rules or some mathematical framework to make a decision. So for example, you can see in the image, we have a flower. This is not a real flower. Of course, it's something that people have done with their own hand. And you can see on the right, you see the contour, and it's very clear the edge of the object. So for example, we have some, so people developed at that time some mathematical method, like for example, what they call the curvature signature, for example. So given a contour, for example, they have some algebraic method to identify the shape of this contour. And based on that, they can decide if this is, for example, a circle or a square or a rectangle and so on. So this was the way people used to do computer vision at that time. So extracting low-level feature, and then they come up with some rules in order to get some insight from the images. And here, concerning the decision, I can give an example. I've been working a while back, a long time ago, like 10 years from now, where the problem was about to split some, the rice. So you have some rice on a table, for example, not cooked one, the one that we have just harvested. And we want, for example, to count how many grain of rice we have on the table. So for doing that, I've tried to solve this problem. And the idea I came up with at that time was using the contour of the whole image to get a whole contour. And then when you see the different grain that are aggregated between them, you have some kind of angles. So I look on each of the angle, and I use this angle, in fact, to split them. So it was a very long process. I have to make a big for loop and do some heuristic to decide how to do that. But now we don't do this kind of process. So this is how people were dealing with computer vision at that time. And then I will say in the middle of the evolution, around the 80s to the 90s, people come up with some what they call descriptor. So when they extract low-level features from image, they try to create some kind of vectors that summarize what they found as lower features. And there are many work on that. So, for example, there is what they call the sift and the rob. All these are kind of vector that represent some information about an object in an image. And then given this vector, they use machine learning to now solve the problem. So now if you look at the main change here is from using rule-based, but now they are using machine learning. In fact, this machine learning process forced them to, researchers to let, how should I put it? To formalize the low level features into vectors. So using vectors to represent the contour, for example, using vectors to represent the color. So, and they aggregate all this information about the contour, the color, even the gradient of the image, many information, they gather them into one vector and they feed it to a machine learning model to train it. So there is a very famous example I want to show you. This is the Ha cascades. And Ha was a researcher that created the Ha wavelet. So some researcher, notably Paul Viola, came up with the idea of extracting some features. So for extracting features, he used what we call convolution kernel. So I will come up afterward to explain a bit more what the convolution kernel are. And it used this kernel, in fact, to extract edge lines and kind of four rectangle in the image. And with this simple feature extraction, in fact, it was able to detect face. And in fact, it was the first in the world face recognition system that can be that work on real time. So for the first time in the history of the computer vision, this guy invented in 2001 with this simple feature extraction and using SVM. So he used SVM on the features that he created, so a vector of features. And using both, he was able to detect faces. So you can see down the screen here, if I can try it, for example. So here you see the detector, it detects the face and even the eyes of a person. So very simple idea, but powerful because now they use just some feature extraction, no headaches with heuristic, how to put things together, only the machine learning, learn things and find automatically the eyes and the face directly. So this was one milestone at that time in the evolution of computer vision. Then coming back to the last part, which started roughly in 2012, the revolution of computer vision with AI. So in fact, this AI revolution that we are seeing now, we are all talking about AI everywhere. It started, in fact, in computer vision. So it was the milestone that has been reached in computer vision that create great attention to the field of AI and deep learning, and people trying to stretch it to apply it in another fields like NLP and so on. So in fact, it started all by computer vision. So, and the model that people come up, or the new method is now that we will not do the feature extraction manually, but we let the algorithm itself learn not only the feature, and then it will learn the task at hand again. So you see now, like the machine learning is eating every part until now. Until now, we are at the level that we don't anymore think about how to extract the feature manually. We just set up the stage and we let the algorithm do everything. So hopefully this give you a brief overview of how things are going on. So we are kind of automatizing every part of the process until now the whole process, I would say, is kind of automatic. So after that, I wanted to perhaps mention rapidly, so concerning computer vision. So because now we have a mix between computer vision and AI. So before it was, I mentioned the story, it was purely, calculation of the math on the images and doing some heuristic, some kind of rule based to derive some insight from images. But now it's more about using artificial neural network. So how this marriage, I would say, come up. So it didn't start, in fact, in 2012. In fact, people are starting to use neural network where they just flatten the whole images, that is 2D, into one vector and feed them to neural network. But then in 1979, so the first CNN has been invented by the Japanese Fukushima. So sometimes I found that people don't know, people most of the time talk about Yann LeCun, but the person that invented the CNN, and you name it at that time, the neoconitron. So in fact, it just removed the, I would say, dot product that we are used to see in the neural network or the matrix product, and you use instead another linear operation, which is the convolution. And using that, he was able to analyze and get some good result. But at that time, he was not using the propagation algorithm that is well known and very powerful to update the weight of the algorithm and get better result. So this was the first person that created it, and he used the convolution as a linear operation. And then we have in 1986, Nain LeCun that came up with I would say deep learning that we have now. So basically, it's the same structure that we have now since 1986. And he came up, in fact, with the first industrial application, because the system was able to recognize handwriting digit, and it was used in the US to read check automatically on ATM. So people were using it since that time in the US. And then we have, as I mentioned, in 2018, the famous ImageNet competition where Geoffrey Hinton and his team came up with a better model that gets the best result, and that, I would say, activated or triggered the revolution of AI. So after giving this overview of how we feed the computer vision and artificial neural network get involved together, let me go to explain a little bit the operation of convolution, which is very important for images. So there is this website, Image Kernel, where basically first we show here the real image, which is very small here. You can see a very small image. But when you make it bigger, you start to see the pixel finally individually. So we can see the pictures. And here is what really the algorithm or how the image is represented inside the computer. So it's just a matrix of values. These values range from 0 to 255. So 0 means completely black, gray in the middle, until 255 where it is completely black. So you can see here, for example, it's completely black, and you can see 255 on the square, on the red square on the image. So this is how the image is represented basically in the image, in the computer. So a computer does not see what as human we see, but it just see what is on the left. So the the operation of convolution, in fact, is a local operation. So basically how it works. So when we talk about convolution, we talk most of the time about kernel. So we want to do some operations that are local. So we have to set how large is this locality, in fact. So this is what we call the kernel. So the kernel is, in fact, the term that we use to specify this locality. And it has a size. So it can be a locality of 3 by 3, 5 by 5. Most of the time, we use an odd number. So basically an odd number, because most of the time you want to do an operation on a pixel based on what is around him, like on the neighborhood of this pixel. So because image normally they are, I would say the information in an image is local, in fact. So to understand, for example, where the eyes, you have to look at around here where I'm turning the red square on the image. To understand the eye, you don't have to go up here to understand what is an image. So the information in the image is local. So that's what researcher understood and guide them to do, to understand that in order to get a better information about one pixel, it's better to see on the neighborhood of this pixel to have a better idea of what's going on around this part or around this pixel. So that's the idea of the convolution. So getting some information about one pixel based on its neighborhood. And it works like doing some set of operations. So we just add, multiply the pixel with some values and then sum them together. So here, for example, there are some predefined, what I will say, predefined kernel. So if I put here identity, for example, which is 1, so here you can see the kernel on the left. You see, so on the middle, so it is a 3 by 3 kernel. So on the middle, we have 1 pixel and we have the neighborhood. So we do some operation on this pixel, which is the center, and the neighborhood, and we get, as a result, 1 pixel, which is the red square on the right. You can see here. And which operation is done is what you can see here. So for the identity, let me say it again. So the identity here, let me take this part around the eyes here. Yeah. So the different value of the pixel are what you see in the square. And they are multiplied by the values of the kernel. So you can see on the first row, we have 0, 0, 0, because I'm doing identity. So I want to replicate the same pixel. So again, on the second line, I have 0 on both sides and 1 on the middle, so that the same value of a pixel will come after, and then I have 0. So if I do the multiplication and I sum them, I will get only the value of the initial pixel. So this is where things become very interesting, because, for example, if I ask you to tell me what are the main things that characterize sometime an object, for example, a table. What are the main things that characterize a table? If I ask you this question, what will be your answer? Can I have some answer, or? Hello, are you following me?
Yes, we are following, Ishmael.
Okay. Okay, so I will go ahead. So I will say, for example, we can say that the shape, for example, how the lines are together, so how the lines are gathered can indicate to me that this object is a table, for example, or this object is a mug, for example. So here the idea is to, for example, try to see the difference between what pixel is in front and what pixel is behind. So this is simply a kind of derivative. You know, the derivative is you take f of x plus h minus f of x, and you divide it by the step, which is h. So we can do the same thing with the image. Let me, for example, here, with this image, where we are already set the identity, let me try to do one thing. So I'm on the image, I'm on, suppose for any place in the image, I'm on this pixel at the center. So given here, for example, where I put the cursor, I put this mask over this part, for example. And what I can do, I can look on the right to see which is the pixel value on the right and what is the pixel value on the left, and do the difference. It will be a kind of derivation, but along the x-axis. So I can, for example, here, so use a custom one and put here +1. Here I just put 0. And here I plus -1. So for each pixel, at each place, I take the pixel that is after minus the pixel that is before. And you can see here how the image is completely black, except the edge, where the image intensities change a lot. And this is how I get the contour, in fact. So the basic idea of the contour is that I'm doing some derivative to see where things are changing the images. So this simple operation, in fact, can help us get these low-level features in the images. So there have been more sophisticated method to do that, how to come up with a better kernel. So this has been researched for years and years. So people can stay 1 year, 1 year and a half to come up with just some value in this. So this is how people was working before. So 1 year for getting the kernel, so that we name after the people that discovered them. For example, we have the Sobel filter, we have Kane filter, and many filters for finding the edge in the images. So I can put, for example, this one, the outline, that take the kind of difference in every direction. You can see at the center we have 8, and on the border you have -1, -1 everywhere. So when you multiply -1 on the neighborhood, on the 3 by 3 neighborhood, by -1, and then we will subtract it from the 8. If you look, 8, if you sum all of these, you will get 7. If you sum up all of them, you get 8. Excuse me, 8. So -1 here, we have 3. And here you have 5. And then you have -8. So it will be a kind of difference, in fact, in every direction with the center pixel. And here you can see we get more edges. And this operation of convolution is very powerful. And this was, in fact, what Fukushima come up with, and they combine this with the with the neural network in order to come up with the CNN, what we call CNN, which is convolutional neural network. So hopefully you get an idea about what is the convolution operation, because it's very important. And today, even if you have better architecture, but it remains one of the most widely used kind of, I would say, architecture or model in deep learning nowadays. Okay, so after explaining, hopefully you get a rough idea about what is the convolution operation. Now we will go back to our presentation and try to do an end-to-end application where we try to solve a problem using deep learning and using what we do nowadays. So the modern way of solving computer vision problem using deep neural network. So let me come back. Sorry, like I can't get. Okay, so hopefully you can see my screen. So here I will present you one work I did on breast cancer diagnosis, and which is a computer vision. So because we are analyzing images, and so we have many kind of image. So as I'm more familiar with this work, and I want to share with you, so you can use it deep learning for solving different tasks in computer vision, not only in the medical field, but also, for example, plate recognition for cars, for example, because sometimes in the traffic, we want to identify people that are running too fast and, for example, sending them some kind of, we say, what is the word for that? Like, because sometimes on the traffic, we have some Vites limit. If you go over it, we have some kind of, we say kind of punishment, not punishment, but you have some kind of fees to pay because you did not respect the rules. So in this kind of situation, so we can use computer vision to automatically on the traffic detect the car plate. And most of the time, with the car plate, we can identify the person that is driving his car. We have some quality information and try to register them as doing an infraction in a given area. So, for example, I'm giving this example because this is what is being implemented in my home country now in Cote d'Ivoire. So people are doing it manually, and we are trying to convince our government to let the researchers come up with some solution to do it locally. So let's come back to the main problem here. So here we have a data set coming from one competition that happened in 2018. So perhaps I can show the website so that you can see that. So this was a competition that had been organized in order to classify the different breast cancer images in the different category. So, you know, during the diagnosis, we do what we call the needle biopsy. So they put a small needle on the part of the breast of the woman where we suspect to be a cancerous region. And with the needle, we have a small sample of the tissue. And using this small sample, they have some technique to get the image out of it. So this is the kind of image that is used for this challenge. So these are some example of image based on the tissue that has been that have been collected from different person that are at risk of having a breast cancer. So coming back, no, sorry. Okay, so I will give you all the links. You can go and so have more information later on, because the time is stretching a little bit. And so basically, we call this image histology image, and they are very large. So you can see 2,000 by 500 images, and you have to classify them into 4 categories. And for doing that, so basically the competition has 2 parts, the segmentation part and the classification part. But in our work here, we are going to focus on the classification part. So what we do first, so I put some code for downloading the data set. So you can use it yourself afterwards, and so follow the different steps to have a data set on your own Google Colab drive, or your own drive, and you will be able to run the code smoothly. So, and here we do a minimal exploration and then do the partition of the data between training and validation set, as I mentioned here, but not so trivially. And then set everything so that we can be able to run our model and make some prediction. So here we are going to use Fast AI library. So so I put the instruction to download it, and also to import some libraries and some method classes. Here I'm collecting to my drive. So this is the part where you are going to download your data. So me, as I've already run it, so I put it here. So you can just put your username and your password in order to do that. So I mentioned the different step here. You have to go to a website and to register, and then they will send you an email with with your credentials, and you'll be able then to download the data set. So me, as I've already downloaded them and they are on my drive, so I just access the folder on my drive, which is in the Colab notebook folder inside data batch 2018. So here I just show to see if everything is in place. So there are basically two folders: the WSI, which is the images for the segmentation, and the photos are for the classification. So inside the photos, we have basically 4 folders. Each folder is for one category. So in situ, invasive, benign, and normal. So these are the 4 categories. So for basic exploration, here on the website, they give us one file. And this file is very interesting because it informs us about, is a metadata, in fact, from which patient the data that we are seeing come from. And this is very important to know what images belong to which patient. So this Excel file looks like that. So you have the image here, and we have the label and the patient. So there are some patients where there is no ID, and they mention on the website that for this patient, we can assume that each image come from one different patient. So that means this benign image B001 TIFF belongs to one patient, and the B002 belong to another patient, which is not the first one. So we can consider that every patient without an ID is a different patient. So this is what they mentioned. So here I just try to figure out, so what are the images that belong to some patient that are well identified with some IDs. So here I just show some data here, but more importantly, so I show some image. I try to see the distribution, more importantly, so of images per patient that are identified or patient that have IDs. So you can see here, so we have ID 14, for example, that have 36 images, which is a lot. And some others have basically perhaps 2 or 1 images. And of course, the rest that does not have any IDs will not, they are not going to show up here. So, for example, I was very interested in this patient, ID 14, to see the distribution of the image. So we can see that the patient, for example, have image in different categories, like benign, in situ, invasive. So this can be explained by many reasons. For example, there might be some part of the breast that has the cancerous, where the area is cancerous, and some area are not cancerous, for example. Or perhaps it was a longitudinal study where the patient came and then she came afterwards, and perhaps she developed the cancer through time. So this can have many meanings. But at least we understand that some patients have data across different categories, and this is very important. So here I just try to show some images. So after you can read the text, and I made some comment along the lines. So let's go straight to the partition. So here I mentioned building a robust validation set, because there is a problem here when we identify that some image belongs to one patient. We have many images for one patient. And we are trying to train our model and want to see if our model can generalize to other patients, to other image from other patients. So if I take, for example, patient with ID 14 that have 36 images, if I just do our simple train test split randomly, what can happen? I can have patient ID 14 having 20 image in the validation set and 16 images in the training set. And even more, it can be from the same category, because we have seen that it has many images. For example, here in the distribution that we have shown, it has more than 20 images of benign. So suppose we have half of them in the training set and the other one in the validation set. So if the model has been trained on the training set, and it has seen the image from the same patient, from the same category inside the training set, and you use the same model to predict the 10 other images that are benign in the validation set, it will be trivial for a model to detect it. And this will bias your score. This is what is important here. Because you have a very good score, you say, whoa, so I'm getting a very great score. But in fact, you are fooling yourself, in fact. Because the model, the way you partition the data between training and set has a bias in some patients, so that some patients already have some image on the validation set. That means they are already seen what is inside the validation set. And this validation performance that we'll have will not be correct at all because you did not sample correctly. So this is what I want to emphasize a lot. When you are splitting your data in between training and validation set, it's very important to pay attention to the way you sample them. You have to identify the different, I would say, categories or strata in which lies the data. So here we have the categories, but we have also the patient ID. If it's another data set where we have on it, for example, on top of it, the sex of the person or the city where the person is living. So you must be sure to try to sample across the different what we call strata, so that in your validation set, you will have something that represents the whole data set. So the whole idea of all the code that has been written to go faster is to, when, for example, I put one patient on one partition, for example, I will put all the image associated with this patient inside the partition. So for example, patient 14, if I take the images of patient 14, I will take all the 36 images inside the training or inside the validation set. So this is the main idea of the code that I've been written here. So the idea is just to be sure that I'm able to put all the image associated with one patient on one partition at a time, not both, so that I will avoid to make the split blindly and have a bias, or what we call sometimes data leakage. We call it sometimes data leakage. So to avoid this leak, we do that. So you can read the code afterwards. And so afterwards, I can see that I have a balance validation set where I have 20 images per each class. And I'm sure that for each image that I found here, they belong all to one patient and they're only inside here. So this is the first part about the data partitions. Then we go to the second part where we are doing the training. Okay, so basically we do the same thing again. So installing the library, calling the different method, and setting the different path. And with Fast AI, we have a method where you can use the CSV file that you have created in order to automatically load all the data. So here, I will say the library handle heavy manual work of setting the different path, reading the different images. So you just specify the path and the folder inside this path, and then the data split CSV. And then I specify the column that belongs to the image. So where I specify, I have the image name, and then the column of the label.
Apologies for that too. You have less than 10 minutes, so I don't know if you want to quickly wrap up so that we can take questions. I think we have some questions that we want to take. So because of our time, yeah.
Wow.
Yeah.
So let me try to rush rapidly.
Okay.
Yeah. So having the image inside the model, so nothing more. We use one architecture that we call the ResNet model with 34 layers. And we have a metric, this is the error rate. And so we use what we call transfer learning, so which is a method that, in fact, is about using a model that has been trained on another task and use it for another task, for a second task. So hopefully we have seen it a lot in NLP courses, and the same I would say the same idea of transfer learning. In fact, it started by computer vision. It is in computer vision that people discover it, and they apply it afterward in NLP. So I'm using this one, and trying to train for one epoch, which is a whole roundup on all the data. So here I trained for a few epochs and I was getting like 20% of error, 25% of errors, and I saved the model. So basically, you will read the code and you understand it. But what I want to emphasize again is the analysis, because sometimes we rush on training model, but the analysis is something very important. We should focus on it as well. So we have a way to report the different precision we call F1 score. You can see here. And for each class, for example, we can see here that the Benin class is performing the worst among the others. We also have confusion metrics so that you can see how many images are misclassified and so on. Also, you have a method called most confused, where you can see, in fact, the Benin class has been confused 6 times with invasive. So say a class is invasive, but our model predict that it was Benin. So 6 times. So these are tools that can help debug your model and see how you can improve it. And also we have a top loss. So the loss is a way to measure the errors, but in a way that is learnable by the model. So you can see some of the images. So here you can grab a pathologist with you and discuss with him to see, so how does it make sense or not. And finally, I will wrap up, I will finish with the last part, which is explainability, which is something very important. In fact, it can help discover some important things. And I mentioned last time the convolution operation. So people found out how to project the result that we get at the end of the neural network to see what, in fact, part of the image has influenced most the score that has been obtained, or the class that has been found by the model. So, for example, I apply it on this image, this single image. So this single image has been classified as in situ, while the image, in fact, is not in situ. The image was, in fact, Benin. And I have some library here that you can download and read slowly. I even put, I think, a link where they explain different methods, GradCamp book for explain the model. And what is interesting here is that applying it on this image, we can see which part of the image the model draws focus more to get this result. And you can see that it is this part. And this part, if you look at here, is this one. And this is what is interesting, because now, as I say, you can grab, again, the pathologist and say that this is what the image understood, according to your knowledge. Is it correct? Or perhaps if it's not correct, the pathologist can investigate more to see, this I've never investigated. Let me investigate. And in fact, some people discover, in fact, some things in breast cancer, in the field of breast cancer, that's the root cause was a deep neural network that found the part of the image, and people start investigating and found that, what the neural network found, in fact, was correct. So this is something very powerful, again, with the neural network. Not only you classify, but you understand why you have this result. So hopefully you have a very good idea. I'm sorry, I didn't split the time correctly so that we'll have more discussion on this training part. And yeah, so the notebook is very, I've tried to make it clear. So I hope you will be able to follow it and to replicate the result and try to make it better, get a good result. And then I will stop here.
Well, thank you, Dr. Ismael. So we are really way behind time. Okay, so thank you very much. I think, like you said, we expect you can share this notebook with us, so we can go ahead and also share with the participants. And if there are other questions, I'm sure we can always get back to you, since that would be good for us too. I mean, for that question. So, but before we go, we have a question here. So I think there's a question here on so the question is, in kernel calculation, how do you derive values So did you get that?
No, can you repeat, please?
Okay, well, can you hear me clearly?
Yeah, yeah, I can hear you.
Okay, so in kernel calculations, so how do you derive the values? So that's the first question. Then
Okay.
maybe we can then proceed.
Okay, so I can proceed with this question.
Yes, you can proceed.
Okay, yeah. So good question. In fact, the kernel, the values are based first on, I would say, some research, in fact. So in fact, it started by what I mentioned you. So the way we derive, how we derive locally in the image. Let me, I have the kernel, yeah. So I use the custom kernel here when I was presenting. So when I use 0. So the idea, in fact, is to get, for example, the edge. Most of the time, the kernel, they use it to get the edge. And the edge, in fact, is when the values change a lot. This is the idea of the kernel. Because when you do know that this is the limit of the table, because after, for example, a table, you have another feature. You have, for example, the background only. We have, for example, a bag that allow you to understand that you are not on this object anymore. So the idea was to find a better way to get all the edge, and people start to change the idea. So people started with this small derivative in one direction. They start to do, for example, the same thing in another direction, so that we can get, for example, here a better one. You see now it's more better than the one I use only the X direction. So it was really a painful process. So people have to trial and error to come up with good method. So this is how it was working before.
Okay. Thank you very much, Dr. Ishmael. So
Welcome.
I've also been notified that we can accommodate additional 30 minutes, at least for now. So do you want let's continue? Okay, so Dr. Ishmael, that means you can still extend the class for the next 30 minutes, and I can come back and we just wrap up with you.
Okay.
Yeah, thank you.
You're welcome. Okay, so let's go back to the notebook. Okay, so basically, I would say, so I've already talked about this part. So I think the code is self-explanatory, and also the documentation of the FastAI is very clear on that. And what is very interesting about that is you are not going to type manually the code for doing visualization, because visualizing your data is very important. And FastAI handle it for you. So for each image, we have a class associated so that you can have a better understanding of your data. And here, so I've created what is called a model. So the model here is a big object, in fact, because to train a model, you need the architecture, which is the structure of a neural network. Then you also need the data as well for training the model. And you need some other settings like how do you measure the errors? How do you measure your loss function? Because loss function is a function that enable you to measure your errors, but in a way that is differentiable, so that you can update automatically the weight of your neural network. So you have it. So in FastAI, you have many defaults. So I just specify what I want to customize only. So I want to customize the data that I'm using. I want to customize the type of architecture I'm using. and then the matrix I'm using. And for the rest, if you look at the code, you will see there is a lot of default, so a lot of them. But you can go on the documentation and see gradually if you want to use them and so on. So when we train our model, so we have this output here that show us which epoch and the loss on the training set and the loss on the validation set. And here we choose the error rate, which is in fact the opposite of the accuracy. So is 1 minus accuracy gives you the error rate. So that means we want to decrease the error rate so that we are very close to 0 to be sure that what the model is outputting is very close or matches directly the expected output. So here we train, so with this fine-tune, as I mentioned, which is a transfer learning. So to perhaps expand a little bit on it so you get a good idea. When the ImageNet in 2018, the researchers came up with the first deep neural network that won this competition. In the next year, or before the next year, some researchers was interested by this result that were very extraordinary. So they look at inside the network to understand what is going inside the network, and we are getting these very good results. And for doing that, they look at the let me perhaps show you this other slide. So can you see my screen? So I talked to you before about the kernel convolution. So the convolution neural network, we have some small kernel on the first layer, and the second layer, we have also the small kernels. So basically, if you can see the image here, there are some researchers, they come up with this article, Visualizing and Understanding Convolutional Neural Network, that have been published in 2013, like the next year after the ImageNet. And they found that the first kernel was doing kind of what people were struggling with, like detecting edge. So people were taking like 6 months, 1 year to come up with some set of weight in the kernel or some set of values in the kernels that can extract some edge and importance features. And they found that the neural network, in fact, was finding these kind of things automatically. So this was one striking result, because people were thinking, oh, you were spending years and long time to come up with these small kernel values, and these neural networks had just learned them how to find them. And they find that on the first layer, it was detecting this pattern. So like kind of edges. So like here, it can detect an oblique, I would say an oblique segment, like an oblique line. So these kernels. So this kernel, for example, they detect colors. So the orange, if it matches orange, it will activate. We call it activate. So this has, here they detect what has the grays, and here again, some other lines. So they move on to the next layers. They found that the next layers were able, in fact, to detect interesting patterns, like multiple lines, like this one, for example, multiple horizontal line, vertical lines, also multiple horizontal lines, and even some small circles, like some dots or small circles. And if you notice something, you have small lines, you have some edges. If you combine two edges, you get a corner. Or if you combine many vertical line, you will get this pattern. So it's like the second layer is combining the different features that have been found in the previous feature, the previous layer. And even for the cycle, because we can, take a cycle and make it like so we can get a cycle out of small segments. So we can draw small segments in order to get a whole circle. So here we understand that the previous layer that was able to detect like a small edge, combining the small edge that are kind of that have a kind of curve, combining all of them, we can get a circle. And this is what the second layers of the neural networks were able to detect. So that's become very interesting. And then afterwards, we see that some more advanced features that are based on the combination of the previous ones are detected. So now you are able to detect human face, the head of a human, even the upper part of a person. Here we can get some kind of mosaic, if I can say it like that, some repetitive motif patterns. So we start to see very interesting patterns. And this result of this researcher, when they found it, they say that, okay, so what is interesting is that it's getting this edge. And this edge, combining different edge, we can get multiple shape, different shape. So they start to think it based on the fact that for any computer vision, most of the time what we were doing before is always using the low level features and then combining them and try to come up with some insight. And the neural network is doing the same. So if it has already learned to detect the low level features, why should we relearn them again for another task, for example? Why should we relearn that? It's kind of waste because it already know how to detect an edge. And even if I'm not trying to finding people, if I want to find a car, I still need some edges. If I want to even the example that I'm showing for diagnosis for cancer, breast cancer, I need some edge here to understand the structure inside it. So they say that, okay, so why not freezing this weight that has been already learned? And then we will just learn the upper part, which is more advanced features. And this is how they came up with the idea of transfer learning, because the first part of the network has already learned some generic features that are always useful for any task in computer vision. And what's happened, in fact, is these researchers, in fact, what is very, very interesting, when they discover it, they use the transfer learning for the first time to compete to the next year, to the following year of ImageNet competition. And they won the competition. Because this was the secret sauce. They found it, and they applied it, and they found a very good result. And from that time, the transfer learning has been very popularized. So we are using it every time. Even now, we use it in NLP. So this is the idea of the transfer learning, which is a very powerful technique. So we just call it on one line of code, but it has been the whole body of work of investigation by researchers to find it. Yeah, donc sometimes when you look at these libraries, in fact, they are packed of a lot of work. So using this, we are able to get very good results at the beginning, because training from scratch, we will have, after few epochs, we'll have a lot of errors. So I'm sure you have a lot of errors, but with this approach, we are able to get very good results in a few times, and also with less data, because deep learning are notorious in data because they have many parameters, and in order to learn, we need more data to learn with parameters. But thanks of the transfer learning, we don't need as much of data like ImageNet 1.5 million of images. Now, even we are training our model here with roughly 200 images, and we are getting some good results. So after applying this, so we get to the point where we get we have 25% of errors. And so I put here how we can save your model, and you can load your model so that you are not going to retrain again from scratch. So with this library, even you see where your model has been saved. And now concerning the analysis. So I'm sure you are a little bit familiar with this F1 score recall. So I'm not going to get deep into it, but the F1 score is very important when you have a balanced data set, a disbalanced data set, an imbalanced data set. So the F1 score is better. If you use the accuracy when you have an imbalanced data set, you will have not a very good appreciation of your model. So the F1 score is very useful when you have imbalanced data set. The confusion matrix, I hope you will know as well. So here you have the predicted here, and here you have the actual classes. So when they match all on the diagonal. So the diagonal shows us what has been correctly classified. So for the Benin, we have 11 images that are correctly classified, but we have 4 images that has been classified as invasive by our model, while they are Benin. So this is an error, for example, here. And the same goes for in situ and so on. So this is basically the idea to understand why your model is not performing very well. Even though here we have the F score for each class. As I mentioned, the Benin one has not a very good score. And the most confused, I think this is something interesting, because here you see the Benin class, our Benin class here, our model classify an image as Benin while it is invasive. So we want to know, in fact, which class has the most misclassified, for example, images. So this is what the most confused is about. So you will get here when you specify the minimum number of images that has misclassified. You specify them, and it will show you, based on this minimum value, how many images has been misclassified that are more than 4 images. So here we have the Benin, which is in fact invasive. No, sorry. The opposite, in fact. So it is a Benin class that has been classified as invasive. So we have it 6 times. Also, we have a class that has been classified, or that is in situ, but has been classified as invasive again. So this, based on that, you can know in which class your model is underperforming, and try to think a little bit more about, so what should I do? For example, here, you can, for example, try to see which images are concerned by this problem, in fact. And this is where the top loss comes in, where you can see on which image you have a loss which is very high, while the model is confident in the result. So, for example, in the first image here, let me make it bigger. Okay, so you see here, we have the prediction that has been made by the model. Then you have your actual class. You have the loss, which is the error between your prediction and the actual result based on the internal of the model. And then the probability that has been given by your model. So you see here, the prediction is normal, but the class is in situ. And the loss here is 9. So 9 as a loss is huge, because you can see during the training, the different loss are in the order of 1 and less than 1. But here you see a loss which is 9. And again, we see how the model is confident of the probability that this class is normal, is very confident in that. So given this result, you should ask your question, so why the model is giving me this bad result? So it's very underperforming on this kind of image. And if you are in the process of developing a model, this can give you some hints about if I should collect more data about this specific class, or I should get more diverse data, perhaps on this specific class, in order to make it better. So these are way you can debug your model, because the most difficult part in deep learning is not how you set your model, in fact, is how you make it doing what you want exactly. This is the most difficult part. And you have many things to do in the process. And sometimes you are kind of, I would say, lost, because you have many possibilities. But this kind of assessment can give you the right path to follow in order to make your model better. And so given that this top loss, you also have another tool, so which is the GradCam, which is very, very, very important in explaining what your model is doing. Because people mention a lot, you will understand, or you will see in social media a lot, that deep learning are black box models. They just give some result, and we don't know how we get these results. So this, in fact, it makes difficult to apply these models in some settings, like, for example, in the medical field, where people are very sensitive, they are very cautious, and they don't want to make some errors, and they want to be very sure. And this is normal. We are talking about human life. We are not talking about playing a game. So in this situation, explainability is more important than the result, in fact, because we are not looking for 99% here. Most importantly is why, because we are doing science. And this explainability is a very powerful tool that allows us to understand what is going inside the neural network. And in order to better understand it, it has come to the kernel that I mentioned, because the kernel is responsible to extract the features. And the features are going to go through the whole network. So the question is, what part of the image leads to this result? And hopefully you have seen the algorithm of backpropagation, which is just a composition of derivatives in the neural network. So using this derivative, we are able to evaluate the variation of each parameters regard to the result. So when you backpropagate the errors, you will just start by the last layers to see the last layer. I'm talking about the last layer before the classification layer. So the last layer, you will have some set of weight depth, and you will understand how each of weight variation will impact the final result. And you do one step back again in the neural network. And you can do that until getting to the image. And most of the time, when we are training the neural network, we don't modify the image because the image is the things that is natural. We don't have to modify it. It comes from the nature. But with this method, the idea is to see how the variation of the image impacts the result. And people come up with the idea. And with that, we can see which pixel contributed most to the result that we found. And this is what we found. I show here. It's like a heat map where it is more red means this is the part that contributed most significantly, to the final result. And as I mentioned, this can be an opportunity in science to make some discovery, because now with the deep neural network model, we are able to process large amount of data. And we as humans, we have a brain. Our brain is very, 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 very clever and very smart, but it can't hold a lot of information at the same time. But the neural network is kind of able to process a lot of information at the same time and try to put them together. So this is where, for example, as humans, we are not very good at having a lot of information at the same time. So given a lot of images, the model can try to get some insight about what are the driving factors of a given problem. In our case here, what are the main things that leads, that's one the main thing that leads to the result. And here, when we find this kind of results, it's very interesting to go to the pathology to see. So I don't know science, I don't know your field of your domain of study, but this is what the neural network found. Do you agree with that or not? Sorry, I think I have not been active, and finally I haven't deconnected. So this is where I call it the human and machine collaboration happen when we are doing explanation, because the domain knowledge expert will come and we show them what the neural network found, and they will assess, is that correct, acceptable? Does it correspond to my knowledge? If yes, then you can trust the model. Otherwise, you can't trust the model. So this is how we can make our model to deploy them so that they can be used by people in the real life. Because if we are not able to explain our model, we will not be able to convince people to use them. So I think I will stop here. So I put a bunch of other methods, but you can afterward look at it. So I was even able to train more to get at 70% of errors. So that means if you train more, you can get more results. And hopefully, yeah, you yeah.
So I think we might need to just wrap up now and just allow Steve looking all of what we've learned. So please, can we all just appreciate Dr. Ismael? Inside online. Let's appreciate him. So thank you very much, Dr. Ismael, for that wonderful session. On behalf of everyone here, we want to hello guys on house. So on behalf of everyone here, we want to say thank you, a big thank you to you for coordinating the class for over an hour. I mean, that's so much a big one. So thank you very much for giving a lot of yourself to this. So I'm sure we're going to have several questions which are going to come in afterwards. And
okay.
So I'm sure shortly we're going to pass it across the team. They're going to lay their hands on it, and I'm sure if there are questions that get to emanate from that, we definitely communicate those questions to you so that you can help address them. So just a part of us saying thank you once again. Thank you so very much. We appreciate your time, your resources, your commitment, and really giving all of you to this. So once again, for the final time, thank you, and thank you very much. So we appreciate and we want to wish you a lovely day ahead on behalf of everyone. So thank you very much. Let's appreciate Dr. Ismael.
Thank you so much. Thank you. It was a pleasure. Yeah.
Very much. Bye.